In section 1.1, we'll be looking at functions. Our objectives in this section will be to evaluate and use functions, including functions given by equations, tables of values, and graphs, just all sorts of representations of a function. Well, we'll be looking for the domain of a function. We'll use piecewise functions, graph those and evaluate those and see how they play a part in the world of functions. And then we've changed some of these. We're not doing this one. Oops. Not doing this one until later. And then we will review the business functions that go along with this course. Those include the price demand, price supply, revenue, cost, profit, average functions, etc. So let's get started. So what is a function? Well, a function is a rule that assigns for each input, which we usually call x, but we can use other variables as well, one and only one, let's underline that, value. And that value is usually what we call the y. So that's the idea behind a function. If I ask you for some quantity, then you have a function if you can only give me the one answer that goes along with that quantity. So that's what a function is. It only has one answer. The notation that we use for functions is based off of this notation here, f of x. And the f right here is the function name. So this function is named f. And the x right here, inside the parentheses, is our input. And this tells us that our input is being represented by the variable x. So for example, when we look at number 1, we have f of x is equal to 5x squared minus 7x plus 6. So that tells me the function name is f, and the rule that is going to assign values by this function says take the input and square it, then multiply it by 5, then take the input again and multiply it by 7 and subtract that first result minus this new result, and then finally add 6. And that's what this function does. Takes the input, squares it, multiplies it by 5, subtracts 7 times the input, and then adds 6 to the end. Now this notation here is very important. This says find f of negative 2. And that means that we want the function value, or the y value, when the input is equal to negative 2. In other words, the x is going to be negative 2. So we want to write this out, and I'm very big on the notation that you use in this. If you look at the rubrics for the homeworks in this course, you'll notice that they always mention the notation, the use of the equal signs, and things like that. So that's something that we want to develop inside this semester. So we want to start off, when you start off answering problems, you want to tell me what you're looking for. This problem is asking for f of negative 2. So we start off with f of negative 2 is equal to, and then we go ahead and we work the process. Now, something that I've been teaching students lately to do whenever they do these problems that has really improved the execution of these is to not just plug negative 2 in wherever you see these x's right here. I'm going to put little boxes around these. But instead of putting just negative 2, go ahead and put in the entire parentheses with the negative 2. What this does is it prevents the order of operations from getting skewed in the process of simplifying the result. Okay, so you always know what is going on between the variables and the other symbols around it, the squaring and the 5 and such. And the order of operations is always maintained. So this is going to be 5, parentheses, negative 2, close parentheses, squared, minus 7, parentheses, negative 2, close parentheses, plus 6. And I've highlighted exactly what I'm dropping in, and I'm dropping those in exactly where the boxes are whenever I wrote the function above. This shows me the multiplication, it shows me what needs to be squared, it shows the sign of the negative 2, of the negative with the 2. Everything is well organized. You work this out and you get 40. And this is the y value, or the f of negative 2 value. If you were going to graph this on a graph, then this information corresponds to the point negative 2, comma 40, the x and the y, that makes up the entire graph of the function f. We'll do some more graphing later on, but I want to make sure that that is clear. The f of negative 2 indicates that negative 2 is the x, and the result of f of negative 2 is the y. Let's look at example number 2. The population of Texas since 1950, written in millions of people, is given in the table below. Define P of x to be the population of Texas x years since 1950. Find and interpret the value P of 40. All right, so this is a very characteristic problem that we encounter. It doesn't use sort of the basic data number for the x input. The x is relative to some other number. In this case, the x represents the number of years since 1950. So let's make that this third column. X is equal to number of years since 1950. Squeeze that in there. And now for the actual year, 1950, we need to come up with the value of x. Well, how many years was 1950 since 1950? Well, that's 0. It's the same year. And then how many years was 1960 since 1950? That was 10 years. And if you continue on, you see the pattern: 20 years, 30 years, 40 years, 50 years, and 60 years. And those are going to be our x values. Then the numbers in the right column give us the population. That's the P of x, because we've defined P, capital P in this case, to be the population of Texas since 1950. And now we want this, P of 40. So P of 40, I would go to where the x is equal to 40, and that's on this row here. And the number looks like it's 17.0. So that's the value of P of 40. Now, what does that mean? So interpret is always going to mean to, number one, provide complete sentences, and number two, express the values in words that are related to the scenario given to you in the problem. So we have P of 40. What does the 40 indicate? Well, 40 was the x. X was the number of years since 1950. So the 40 must be referring to 1990. And then the y value, 17.0, is the P value. Well, P was the population of Texas. So I can incorporate that into a sentence, and I can say the following. In the year 1990, the population of Texas was 17.0, and now you have to be careful. Certainly the population of Texas wasn't 17 people in 1990. What did this population, how was that represented? It's right here. Millions of people. So we're going to go with 17.0 million people. And that's the clear interpretation. Again, the criteria that we're looking for here is that it clearly explains what the results of the numbers are. It uses complete sentences, and it uses the verbiage displayed in the problem above. All right, just make it clear and simple as possible. Example 3 says represent the population of Texas as a graph. So there's a couple of ideas that we want to explore when we talk about the graph. Number one, be sure to label your axes. So we have x and p of x. The domain axis, the x's, the inputs, are the horizontal axis, and the y values, or the range values, are the vertical axis. Provide more information to describe what those values represent if necessary. In this case, the x's represent the number of years since 1950, and the p values are in millions. And also provide the tick marks, right? The labelings here, right? So 10, 20, 30, etc. And then 5, 10, 15, 20, etc. Right? So that's the elements of a good graph. Now we go back to the chart on the previous page, and we just plot these points as best we can, right? So for 0 years since 1950, the population was 7.7. So we'll put that about right there. 10 years after 1950 was 9.6. Squeeze that in about there. And then so on. 20 years was 11.2. 30 years was 14.2. 40, 17. And I'm just graphing the points from the previous page. 20.9, somewhere around there, maybe. And then 25.1, about right there. Now those are the actual data points that were given to us in the chart. But certainly we know that the population of Texas is a continuous value. There's always people here. And so what we can do is we can make the best curve that we can to sort of fit this data. Usually populations grow exponentially. And we know that that's a curve that sort of rises steeper and steeper as you go to the right. We'll just do the best we can in putting those points together, and just do the best you can on that. Make it representative of what the population should actually look like. So it looks like something like this. Next, let's look at the domain of functions. So the domain is the set of values that you can use in a function, all right? Set of values that can be used in a function. And there's a couple of ideas behind this. If we're just doing some basic algebra problem, then, you just get the maximum domain that you can find, right? Whatever will work is fine. But when we start doing business applications and some of these other applications, we do some stuff with farming, these types of things, then you have to take into account the actual physical nature of some of these things. For example, you can't have a price that is negative. You can't have negative fencing yards, right? Or the lengths of the fences. They can't be negative, things like that. So that's where we set up these rules right here. And it says the domain of a function is the set of all real numbers, except if you have a denominator, you can't have any values of x that make that denominator equal to 0. If you have some kind of square root, fourth root, sixth root, any root that has an even index, 2, 4, 6, 8, etc., then the inside cannot be negative, right? That's a no-no. And then the last one is what I was referring to earlier, is the values of x that do not make sense in the context of an application. For example, negative length of a fence, a demand that forces the price of that item to become negative, things like that. We just can't have those. So we exclude those as well. Let's look at example number 4 and find the domain of each function. Part A says f of x is equal to x to the 5th minus 4x cubed. So if I go back and I look at my criteria here, the question is, do I have any denominators that could possibly be equal to 0? Well, I don't have any denominators at all. So we're okay there, no denominators. And then the second one is, do I have any even roots, square root, fourth root, etc., that could possibly be negative? And the answer is no, no roots. So we're good to go, and our base is all real numbers. So we're going to represent all real numbers with an interval notation that goes from negative infinity to infinity. If this information, or notation rather, is unfamiliar to you, I encourage you to go and look that up. Just do a Google search for interval notation, college algebra, and enough information should come up to help you with that. Part B says f of x is equal to x plus 6 over x minus 1. Well, we do have a denominator, so we have to worry about that. The rule for the denominator is that the values of x that we use in the domain cannot allow the denominator to be equal to 0. So to find those x's, I'm just going to go ahead and set the denominator equal to 0. And whatever solutions we come up with are the values of x that would make the denominator 0. Well, this is just x equals 1. And if you tried to plug in x equals 1 right here, you would get 1 minus 1 in the bottom, which is 0. So we can't have that. We don't have any square roots or anything here, so this is the end. So our only bad point in the domain is x equals 1. Now let me show you a little trick for representing the domain. The domain is basically an x-axis. So we're going to represent it with a number line. And we need to exclude this number here of x equals 1. Exclusion is denoted by an open circle. So we're going to have 1 right there. But everything that is not 1 is perfectly fine. And that's on both sides. Now the reason I encourage you to draw it this way and to shade in the good stuff is because it lets you see how many intervals you actually have to work with. We have 2 intervals to work with. And so when you write the domain out, you need to write both intervals. So we're going to start here at negative infinity, and it goes up to positive 1. It's open because we're jumping over 1. We pick it up again and start with 1 and then go to infinity. And there's our domain. Negative infinity to 1, union 1 to infinity. Example C. F of x is equal to 3x plus 4x cubed times the square root of 5 minus x. So in this case, we're looking for the domain. We do have a square root. And the rule is that the inside of the square root cannot be negative. So I'm going to go ahead and affirmatively find what this could be. So if it can't be negative, that means it could be greater than or equal to 0. So whenever we say greater than or equal to 0, we're talking about the positive numbers, and we are talking about 0. And that excludes the negatives. When we solve this, that will give me exactly what the domain should be. So I'm going to move the 5 over. It moves over as a negative 5. And then hopefully you remember this little trick about solving inequalities. If you have to divide by a negative, and we're going to divide by negative 1 here, then you have to flip the sign over. So the greater than or equal to sign becomes less than or equal to. And we're dividing by negative 1, so we get x is less than or equal to 5. We can still draw the number line. We have 5 in this case, but because the equality part is there, we fill it in. And then since x is less than or equal to 5, we shade on the left side. And this tells me that the domain is from negative infinity to 5. And because it includes the 5, we use the square bracket. And that's our domain. Notice that the other parts of this function did not play a role in determining what the domain was. The 3x, we can use any x with 3 times x, no problem. Same thing with the 4x cubed. We can use any x there. Lastly, we have part D. F of x is equal to 9x over x minus 7 minus 3 over the 6th root of x plus 3. So we have sort of a mixture of things here. Let's start with this first fraction. We have a denominator. We have x minus 7. Well, we know the denominator can't be equal to 0, so I'm going to set that equal to 0 and solve for x. And I get x is equal to 7. This is a bad point. We'll exclude it in our number line in a moment. Next, we have the 6th root of x plus 3. And because it's a 6th root, we would set the inside of the 6th root greater than or equal to 0. But where is that 6th root? That 6th root happens to be in the denominator. So because the denominator can't be equal to 0, we have to take away the equality part on this expression, on this inequality. So we have to have x plus 3 is greater than 0 and solve that. So we get x is greater than negative 3. So this one was the double. It had both the denominator and an even root in one piece. We had to accomplish finding the domain by incorporating both aspects of the domain rules. So what does that leave me with? Well, we're going to start with negative 3, and that's open because it can't be equal to negative 3. We're also going to include 7 because it can't be equal to 7. And now we shade in what we want. So x is greater than negative 3 is this piece. We have to jump over 7 and then continue on. So we have that the domain starts at negative 3. It's open at negative 3. Goes to 7, jumps over 7, and then continues on. Let's now turn our attention to piecewise functions. This is an example of a piecewise function. And the reason that we have piecewise functions is because sometimes it's not possible to accurately represent what the function is with one single expression. We have to use multiple expressions. And the way we use those multiple expressions is to declare what domain, in other words, what values of x, we should use each expression with. So what this function is saying is that if my x's are greater than or equal to 1, then I'm going to find the value of the function by squaring each of those x values. But if the x value I want is less than 1, then I'm going to find those values by using the function 3 minus x. So here we go. Let's see how this works here. In our first example, find f of 4. So f of 4, now where is that x value? Well, 4 is greater than or equal to 1. So I'm going to use the top expression. I'm going to use 4 squared. 4 squared is equal to 16. So the value of f of 4 is equal to 16. Now this is a good time to remind you that by the definition of a function, it only has one answer. So you can't say, well, I'm going to use both, right? That would never work because then you would get two different answers and a function can't have two different answers. So you have to pick the one, you have to pick the correct one to go along with the value of x that's being used. Part B, find f of 0. Well, we look at this and we say, okay, is 0 greater than or equal to 1? And the answer is no. And then is 0 less than 1? Yes. So that tells me that I need to use the bottom function to find this value. So f of 0 is equal to 3 minus 0, which is 3. f of 1, well, we look at the values again, and we say, is 1 greater than or equal to 1? And the answer is yes. This is the equality part of this. So I'm going to use the top expression. And we get 1 squared is equal to 1. Part D, find all values of x so that f of x is equal to 4. So we need to find all the x's where it's going to be equal to 4. Well, maybe we can get an answer of 4 if I use the top expression and I say x squared is equal to 4. Well, if x squared is equal to 4, then x could be equal to positive 2 or negative 2. But how is it possible that we could use x squared? Well, the domain that gives me the x squared part of this function is that the x is greater than or equal to 1. And negative 2 is not in that part of the domain. So we have to drop off the negative 2 because it would not have worked inside the square function. In fact, we would have gone to the other function to use negative 2. And you plug negative 2 into 3 minus x, you get 5 and not 4. So negative 2 is out. All right, what about the second part? Well, perhaps we have 3 minus x is equal to 4. If I solve this, I get negative x is equal to 1. And x is equal to negative 1. And that domain was x is less than 1, and negative 1 is less than 1, so this is a good value. So we have these values here, 2 and negative 1. All right. So the graph of y is equal to f of x. So let me write down our f of x function here again, in case we've forgotten it. It's x squared if the x's are greater than or equal to 1, and 3 minus x if the x's are less than 1. Now, there's several strategies. One strategy that you can use is that you can just sort of draw in a little sketch of the whole thing for each particular expression. So for example, x squared is a parabola that looks like this. And if you're doing this, do this in pencil. Looks like that, sort of. And then you go back and you really darken in the part that corresponds to the domain. So the x has to be greater than or equal to 1. So we know that that starts at this point, 1, 1. And greater than is the right side. So we would use this. And then you go back and you erase all of the other stuff that you didn't use. So that's a little trick. I mean, I won't say you're not supposed to do it this way, but it's a trick. All right, now what about 3 minus x? Well, this one is where the x is strictly less than 1. So what I like to find is what I call an anchor point. It's a point that's not really on the curve, but if we had equality at the end point, it would be on the curve. But we can't have equality because we have equality in the other part. So we're really faking it at this point. So you're sort of pretending, all right, what if I could use x equals 1 with this second expression? Well, I would get 3 minus 1 is equal to 2. So that's the point 1 comma 2. And that is going to be a hole. It's an anchor point, but it's going to be open. So 1, 2 would be right here, We're going to make that an open circle. Right there. And then I'm going to graph 3 minus x for all the values on the left side of x equals 1 because x is less than 1. Well, we know that this is a line with slope -1. And we're going to go over lines in a future section pretty soon, actually. So if you don't remember that, that's okay. You can just plot some points and see that it's a line that does that right there. Next, let's review the business functions that if you took 1319, you probably already know these. And if not, don't sweat it. We're going to give you enough information right here so that you can figure all these out. So we have the demand function or price demand function. What this function gives me is the price of item when demand is X. And this is on the consumer side, right? So as consumers demand more items, the price per item goes down. And then the price supply function or supply function is the price of item when supply is X. And that's on the producer side. If you're a company and the more items that you want to supply to the market, the higher the value that you can get for that. That's the price. All right, so here's X, and then here's the price. And so your typical demand curve is decreasing like this. We'll call that demand. And your typical supply curve is increasing, something like that. That's just the laws of economics, right? So the more that's demanded, the lower the price is going to go. Now, one other little side note here, just in case this comes up, and it comes up every once in a while, but the X may not be X items, it may be thousands of items or millions of items or something like this. So just be careful and make sure you understand what is the X representing in this particular problem whenever you do it. All right, let's move on to revenue. The symbol for revenue is capital R of X, and that is the amount earned from selling. Now, selling X items. Now, do not confuse revenue with profit. Revenue is merely the money that is coming in. We have not done anything with our cost at that point. It's merely the money earned from selling your item, period. Now, the formula for this, and a lot of people get caught up on this, so if this is new to you, pay extra close attention to this, because this one formula right here, if you do not understand it, it will definitely derail this course for you for the rest of the semester. I guarantee it, okay? Because it comes up every day that we do this. The revenue function is the following. It is X times little p of X, where X is the items sold, and P of X is the price per item. Now, there's a couple of things here. First of all, it makes perfect sense in the following scenario. If you're going to buy X items and those items cost P, then the total revenue that you have to, send into the company to buy those items is X times P. What's a little bit strange about this that we don't think about very often is the fact that this P of X is actually a function, which means that the price of the items change depending on how many items you're going to buy. I like to think of this as the Walmart versus Sam's Club scenario. What can you buy at Walmart? At Walmart, you can buy one Snicker. And that one Snicker cost $1, let's say. Okay? But then let's suppose that you go to Sam's Club. Well, you can't buy one Snicker at Sam's Club. You have to buy this huge box of 40 Snickers. Okay? Because Sam's Club is one of those warehouse types clubs. But what does Sam's Club do for you if you agree to buy 40 Snickers? On a per Snicker basis, they lower the price. That shows you that the price of a Snickers is dependent on how many Snickers you're willing to buy. So when you buy 40 Snickers, they might sell that to you at 60 cents per Snicker. It's something lower than what they would sell you the one Snicker for. Okay? So that is a recurring theme. And so please take time to think about that. Look for scenarios in your own life where you've had an opportunity to buy this, or you could buy multiples of these, and on a per item basis, it's less, it costs less, the price is less than if you were to buy the one item. You see this in convenience stores where they're selling you the energy drinks and the Gatorades and all that. If you buy one, it's, $2.50. If you buy two, then it's $4, which is $2 per, but you have to buy the two in order to get that discount. And then you can extrapolate this on up for, however many items you want to buy. Okay? Again, I cannot overemphasize how critical this particular equation is to this course. So make sure you understand it before going forward. All right. The cost function, represented by capital C of X, and that's the cost of producing X total items. It's the producers that are doing that. And the profit function is big P of X. Now I emphasize that this is a big P of X because there is a little p of X that we use with the supply and demand curve. So these are little p's. So just be careful that you understand the difference between those. But the profit function is very simple. We have profit is equal to revenue minus your cost. So profit, P of X, is equal to revenue, R of X, minus cost, C of X. So those are sort of the two biggies for this section. And then you can talk about profit or loss. Profit is if your profit function is positive, and loss is when your profit function is negative, things like that. Basic economic stuff. And then we have one more. And that is an average blank function. I left this blank because it applies to all three of these: revenue, cost, and profit. So the average is just when you take that amount and divide it by the number of items that were used. So average revenue is the revenue that you get from selling X items divided by the number of items that you sold, X. And the same thing, average cost when you're selling X items is the cost for those X items divided by the number of items that you produced. And average profit is the profit divided by X as well. So some places use AP, other places use the bar notation. So you could have R bar of X, C bar of X, and P bar of X. So if you're looking at other resources, you might see that notation as well. Either one works for me. Let's look at example number 6. The price demand function for X ray bars, a delicious chocolatey treat, is given by little p of X is equal to 3.2 minus 0.02 X. The cost function for producing X ray bars is C of X is equal to 50 plus 0.40 X. Question A, find the revenue function. So revenue, R of X, is equal to X times little p of X. And our little p of x is the price demand function. So in this case, it's 3.20 minus 0.02x, and that's equal to 3.2x minus 0.02x squared. Notice how I wrote out what we're looking for, r of x, used equal signs, wrote out all the stuff, and simplified it down to a polynomial. Part B, find the profit function. So profit, p of x, is equal to r of x minus c of x. And that would be 3.2x minus 0.02x squared. That's the revenue from the previous part, minus the cost function, which is 50 plus 0.40x. Notice I'm using these square brackets. That's to keep my revenue and my cost functions separate and delineated. The big reason for that, not the first one so much, but the second one. The biggest problem is people forget to distribute this negative appropriately. So you want to make sure you distribute that negative appropriately to get the right profit function. So when that negative is distributed, the 0.40x becomes negative. We're going to add that to the 3.20x, and that's going to give me, let me write it over here, that's going to give me 2.8x. And then I've got my quadratic term in front here, so negative 0.02x squared. The 2.8x was positive, and then the 50 was negative because the negative distributed to it. So I like to keep my polynomials in order. X squared, then the x, then the number. Part C, find the revenue, cost, and profit for producing 100 ray bars. All right, so now we're getting into the applications. When you do the applications, you want to tell the reader what you are finding. So the first one is revenue. So revenue at a selling point of 100 ray bars would be R of 100. So tell me what you're going to compute, use equal signs, and then work it out. So the revenue is 3.20, put in your parentheses 100, close parentheses, minus 0.02, parentheses 100 squared. Work that out on a calculator and you get 120. Dollars. Don't forget the units. Units are very important here. Next, we'll do the cost. So that's 100. So cost of 100 would be 50 plus 0.40 times 100. And that would be $90. And then profit, there's a couple of ways you can do this one, right? You can take 100 and plug it into the profit function right here. But what is profit? Profit is revenue minus cost. And in this case, it's at a certain selling point. So revenue at 100 minus the cost at 100 is going to give me the profit at 100. So I might as well just do that one. So it's $120 minus $90 is equal to $30. And you can double check that. If you plug that 100 into the profit function from part B, you'll get $30. Part D, find the average cost per ray bar at a production level of $100. All right, so average cost at 100 is equal to the cost at 100 divided by 100 ray bars. And what was the cost at 100? $90 per 100 ray bars. And so that's going to be 90 cents per ray bar. Now here's the thing about an average. The average is dollars per something, right? So this is, it costs on the average 90 cents per ray bar to when we make 100 of them at a time. If we make more ray bars, then the average is going to go down because of our fixed cost and stuff. Okay? So the average cost varies based on the production level. It's not a constant. Finally, let's look at part E. Find the cost of producing the 101st ray bar. So it's not asking for the cost of a total of 101. It's find the cost of that particular candy bar, that 101st one. Now here's what's happening. C of 100 is equal to the total cost of producing 100 ray bars. And C of 101 is the total cost of producing 101 ray bars. So how do we find the cost of that exact 101st ray bar? We subtract. We take the cost at 101 minus the cost at 100. And that's going to give me the cost of the 101st ray bar. So if you work this out, you get 90.40 minus 90 flat, and that's equal to 40 cents. So that particular ray bar cost 40 cents. All right, thanks for watching.